Howdy. In this video we are going to discuss artificial neural network implementation with Python. First, let me show you an artificial neural network, which is a multi-layer feed-forward network. In this network I have an input layer, an hidden layer 1, 2, and then an output. So these hidden layer, first and second hidden layer, and then the output layers are the active layers. Basically our model is trying to determine the weights and optimize the result based on those weights, right? So when we are creating a neural network with the Python, we need to decide how many hidden layers are there, and then how many nodes are on each hidden layer, and finally what type of a backpropagation algorithm we are going to use to update the weights to find the best possible results. You have seen actually this example before, so I'm gonna just start by explaining a little bit without going into the details of the code. So I'm importing pandas for data frame. I'm getting also train test split, and this is the file location, employee salaries. And let's look at the file a little bit. So in this file we have an employee ID, salary that we are trying to forecast, actually the age of the age of the employee, whether the employee has an MBA or not, relevant years of experience, and the number of reports that individual has, right? So first I need to decide if I want to keep employee number as an index or drop it from the analysis, which is what I'm going to do. Then I have the MBA, so I need to introduce a dummy variable. Yes, no, that means there are two categories, 2 minus 1 is 1. I just need a single dummy variable, right? The rest is numbers, so I'm gonna just use it. As I mentioned, I'm dropping the employee ID from the data frame, and I'm introducing a dummy variable for the MBA column, right? And finally, I'm saying that my X variables are everything but the salary. This employee has been already dropped. So age, MBA, relevant years of experience, and number of reports are going to be my X variable. And the Y is the salary, right? And next is I'm going to divide my data set into two pieces, training and validation data set. And my training data set size is the 60% of the total set data, and then I'm using random state 2 for calculations. Right, let me execute this one. Right, now the next thing we are going to do is start basically working on the neural networks. One thing I mentioned in the class is that neural networks are very sensitive to input. Think about this situation. I have an age which is, at least in this 5 record, I see between 23 and 37. MBA is going to be a 0, 1. Relevant years of experience is like 1. The highest is 13, and the number of reports is mostly 0. So if I add these things together, which when we are processing the information at a node, we will be adding, multiplying, or squaring and adding, right? So if I add 25 plus 0, 1, and 0, that is 26, but just by age, another entry would be more than enough to dominate the other one, right? And if this is a square, the situation is going to be even worse, because 25 square is going to dominate everything else in this data frame. For that reason, we need to normalize the data or standardize the data. What I'm going to do is bring the data to a scale between 0 and 1, normalize data and reduce the impact of one or few attributes on the overall solution, right? So with that, let me get this get into the pre-processing, right? And I'm gonna call pre-processing and import min-max scalar, right? So what min-max scalar does is, like, for each column it finds the minimum, and then it finds the maximum, and then scales it. And I'll tell you how it is done in this 5. Let's say this is the only 5 record and we have, or 5 row we have, and minimum is 23, maximum is 37, so the range is 14, right? So for each entry it's going to say the cell value minus the minimum, then divide by the range. So 25 minus 23 is 2, the range is 14, so 2 divided by 14 is going to be the value for here, right? Then 28 minus 23 is 5, 5 over 14 is the answer here. 37 minus 23 is basically 14, 14 divided by 14 is 1, right? And then that way it's going to calculate for each one of them, determine max, mean, and then basically the cell value minus minimum divided by the range, right? And then after that it's going to be basically scale everything to be a number between 0 and 1, right? Now one of the important thing here when we are scaling is that you need to remember we have this data set which is divided to training and validation. So when I'm training my data set, it shouldn't know what is in the validation data set. For that reason, when I use the min-max scaler, I'm going to basically train it based on the training data set only, without showing the validation data set. All right, so let me do that. Right, I'm going to call scaler and then say this is equal to min-max scaler, basically, right? And then I'm going to say, actually let me run this line. So next I'm going to say scalar fit, right? So basically apply the scalar function to x train, right? So what did I do? So what I am saying is that basically find min max range for each column using the training data set, right? Then once I have that, I'm gonna say my new x train is going to be scalar, right? Transform. Now basically it knows mean and maximum of each column, and transform the x train, right? And I'm going to do the same thing for validation data set. So scalar transform and x validation, right? So I'm saying that apply scalar transformation to the x validation data set, right? So let's look into this data. Right now I converted to array as well, so I'm gonna call it a data frame, or convert it to a data frame, and then look into it, right? X train, and once it is a data frame I can use the Python pandas functions, which the one I'm using is describe, right? So there are 21 records over there. The mean is here, standard deviation. Mean is 0, as you see, for all, and max is 1 for all of them. So x train is basically between 0 and 1. Let's look into x validation. All right. So minimum is not 0 this time, at least for 2 of them, because I basically determined the range and min max based on the training data set, right? So the max are not also the equal to 1 here, right? And there, and also I have 108. Now these are still very close to 1, right? And that way I'm okay to use this way. Some people try to basically transform the data between 0.1 and 0.9. That way, if there is a slightly larger or slightly smaller number, we haven't observed negative here, but it could have been the case too, then we will be still between 0 and 1, right? That's an option. The other thing I need to remind you that let's say I have a data set and I have training and validation, right? I divided this data set into two pieces. I calculated or run the min max scaler, get the training data set between 0 and 1, and I transform the validation data set. Suddenly I have 5s, 10s, or 3s, and so forth. In that case, I need to check to make sure that training and validation data sets are coming from the same population, right? For example, in this case, I have the salaries, right? Salary, age, blah, blah, and so forth. So for example, I might have a salary information from company A, and I'm trying to do my training based on the company A salary, and then I might go and try to validate on company B's data. In that case, although I might have the same columns or attributes in my model, just because of the difference between the salaries between two companies, I might end up with bad model accuracy at that, right? So I need to make sure that the data I have is representative of whatever I'm trying to formulate for future, right? So that is something I need to be aware of it, right? Now, it looks everything is normalized or standardized. Now I'm going to call from sklearn. We have done this one before for regression, and this time I'm going to call it the neural network, right? And I'm going to import, right, MLP classifier and MLP regressor. So there is a neural network classifier and neural network regressor. So I'm going to choose the regression. Right. Let me try to explain when we do use the regression. So there is a single value. So basically we are trying to figure out this value, right? In this case, we can use the regression analysis, right? If I had multiple y variables, y1, y2, y3, so in that case, usually it's a classification, whether the customer will accept the offer or reject the offer, right? Or this is a service train, core, or opportunistic customer. In those cases, I have a classification, right? So a single, if I'm looking for a single value, it's a regression. If I have multiple y's, then I'm looking to a classification problem. The regression, the next thing is I'm gonna call neural networks equal to MLP regressor, I guess, but right. And now in this, basically, if you press the shift and then the tab, it shows you all the options, and let's try to look into them. Okay. Now, all these are parameters, so I can determine the number of hidden layers. Remember, in the figure I showed you, there were 2 hidden layers. Activation function. This is rectified linear unit. Basically, up to a point, if you are below the threshold value, you don't activate anything, and once you are above the threshold, then you pass that information to the next node. We are using back propagation, but still there are different algorithms to solve that problem. So we are using Adams' algorithm. If you are interested in, you can go look into the documentation for it, and usually there is an article published in a journal, and they have implemented that one, right? There is batch size, learning rate, power, and all these can be basically modified or updated with different numbers. So as we are trying to find the best neural network, this problem, we can basically make changes on those, and then with those changes we will end up with different results. Then we need to basically decide which of those is the best one, right? So for example, let me read logistic, so we can use the identity logistic sigmoid function for the activation, tangent, or rectified linear unit function. So we will start with the logistics, and let me actually start with defining the hidden layer size, right? The notation is that So basically what I'm saying is there are 2 hidden layers, and on each hidden layer I have 10 nodes. You can have this comma here, or you don't need to have it, but the documentation says, if I go back here, there is a comma at the end, so I'm just gonna keep that comma, right? And then I'm gonna say activation is logistic, right? And finally I want 10 times, right? So it's gonna find some weight. With that weight it's going to calculate the regression results, and then it's going to go back and update the weights for these 2 layers, and then go back, that is 1, and then do this one 10 times until it gets as it will continue 10 times until or there is no improvement, right? So let me run that. So I just run this one. Now the next thing is I'm gonna fit, of course, this regression to my X train and Y train, right? So I'm saying I have a network with 2 hidden layers, 10 on each node. Activation is logistics, and do 10 iteration and use this and fit the X train Y train data set, right? Right, so here's the first one is basically Y train. I converted to, when I do the scaling, it converted to a vector, but it was expecting an array. It's not really a big deal. The second one is saying that maximum iteration, in this case 10, is reached, but the optimization has not converged yet. So I could potentially observe a better result if I have continued updating the procedure through the back propagation, right? So how am I doing? I know I'm not doing the best thing because there's still an opportunity, the model has not converged, but let me calculate a few things. First, I'm gonna call from scikit-learn again, right? Import matrix X, and then I'm gonna calculate the R square. I will calculate the mean absolute error, mean square error. Of course, I could calculate mean root mean square error as well, but I think 3 of them would be enough to give you the information. So mean absolute error is basically matrix, right? Then mean absolute error, right? And for that, I'm gonna use the Y again. Let me show you. So it actually ask for the Y true, that is the actual Y, and then the Y prediction. My Y true is Y train, right? And then my prediction is NN predict use the X train, right? So that is basically my mean absolute deviation. Next, I'm going to calculate the MSE, right? It is almost the same thing. Matrix dot at mean square error, right? And then I will just copy paste this one because it is the same structure, right? Finally, let me calculate the R square as well. RSQ is equal to matrix dot R square R2 score, and then the same idea. Let me actually copy paste this, right? So those are the 3 metrics. Of course, I need to also print these and see what are the results. So MAE, MSE, and then root square error, or R square. I think that's what I meant, right? So here's the result. Mean absolute error is like 46,180 on average. Basically, I am off by 46,000. That's terrible. And this is mean square error. And then R square is negative 10. A couple of you guys asked me during the last exam whether R square could be a negative number, or because you found R square, there might be an issue. Now, I'll go back to the formula. Now, can R square be a negative number, right? This is the R square formulation, and let me kind of go over what it means. So we have 1 minus, it says basically yi, that is the actual y, or in this case salary, minus our prediction for that salary. The difference is squared, and then it's divided summed all over all observation or all data, and then squared. And then we have yi, which is the same basically actual salary, minus y bar. Y bar is the average. So if I am really naively trying to figure out what should be a person's salary, the naive approach would be like getting the average salary, and whenever somebody asks me, I would just say 20,000. Let's say that is the average salary, and no matter what the other information I have, right? So that is naive approach. And basically, if your naive approach is better than your forecast or prediction, then yes, R square could be a negative number. For example, let's say this summation is, let's say yi is so different than yi cap is so different than yi. This summation, total summation, is 500, and yi minus y bar is just 100, right? So y bar is a better estimation overall than my individual y cap i's. And in that case, I will have 500 divided by 100, 5. 1 minus 5 is 4, right? So R square can be negative, and what it means is that you are really so bad, you could just tell the average of whatever that variable you were looking, and that would have been better solution than going through all these calculations to get a prediction, right? So in this case, you could just say the average salary for everybody, and that would have been a better solution, right? So what I see here is that R square is negative. If I just said whatever the average was, that is better than me trying to predict all the salaries. Now, one thing here is that we know this in 10 iteration, this didn't basically converge. So perhaps I need to increase the number of iterations, right? Right, and then this one, and then this line, and this line, right? So it reduced from 48 to 46,000. That is a good thing. My R square is almost the same, but I'm gonna do a couple of things to reorganize this so I can run this code a little bit faster, right? And I'm gonna copy this here so they all run together. So that I don't need to just press all those keys many times to run again and again. All right, so 100 basically improved. DD at 46,000. All right, let's do this 1,000. All right, so actually, let me separate these. Right. So when I have the 1,000 iteration, perhaps it reduced a little bit, but I don't know how much. Let me just pay attention this time. 46,165, and I increased it to 10,000. Right, it hasn't converged, so I could probably do more iteration to optimize. So it has dropped a little bit, and I'm gonna try one more and I'm literally just trying. As you see, there is a star here. That means the Python kernel is busy doing calculation. You can also see here kernel is busy, and there was a clock over there showing that it is busy. All right, it's reduced a little bit again, so I'm gonna go back to, let's say, 20. Let's try something else. Let's make these 100 and 100. Right, still it didn't, of course, reach to the result, but and I don't see a lot of improvement either. Let me change to, let's train that way. All right, and I'm gonna calculate. It is almost the same. Can I add another layer? Same. All right, let's increase this one to 200. All right, it didn't do much still because it's not converged. All right, it is doing something. All right, let's change it to rectified linear unit. Suddenly, I was around 45,000, 46,000, and the R-square value was like -10. But suddenly, just changing the activation rule from logistics and tangent to rectified linear unit, I was able to improve, in this case, the predictions significantly, right? From 45,000 average error to 3,000 or so. And I also know that this optimization has not reached the or hasn't converged yet. So I can do 10,000 and see if that is going to help. So let me run. It is dropping. So I could probably try another one here. And then let's see what happens. Right, 25,600. What if I eliminate this one and have just two layers rather than three? Right, and run this one, almost the same. Right, so I could try 200. What I'm trying to say is that as I try different numbers and you are observing it, the solutions changes, right? So that's why actually neural networks require a lot of calculations time, right? And based on which, like right now I'm using, I just changed 3 parameters, but if you remember, there are so many other parameters here, right? Solver, let's try to change the solver as well. Let's see who else is there, solver, right? Let's do LBFGS and see if that helps, right? Solver, right? Right, as you see, that changed the result as well, right? So again, the idea here is that as I try different methods, different parameters, the results I'm going to observe is going to change significantly, right? Earlier, when I used the Adam, it hadn't converged at 25,000, I believe, and then the result was almost, in terms of mean absolute error, 2,500 or so, right? So that gives me a confidence. Perhaps I can just do one more experiment here and increase the number of hidden layer sizes, the nodes in each hidden layer. And now I have 98,000. Let me say what happens if I increase to 1,000 nodes on each layer. It took a couple of minutes. I have edited, so you don't need to wait. But at this stage, as you see, R square is like 99.4, and my average error, mean absolute error, is like 600, right? So that is something, but I could also check this thing to see if I would have something similar on my validation data set, because it is possible that at this point I might have an overtrained network. Right, I'm gonna see, and that's what I was trying to say. So when I did train for a long period of time, 1000 node, 1000 node, and 25,000 iteration, my data or my neural network was performing extremely well for the training data set, but then it didn't do so good on the validation data set because I just overfit it or overtrained it, right? Let's go do 100 again and see one more time how are the results, right? See, at this point when I have the 100 and 100, it is still converged. It is 1600 for the MAE value for training data set. It is almost the same for the validation data set, right? And my R-squared values are also close. So this time I know it is not really overtrained, right? And I could probably try one more thing, and then I'm gonna stop recording this video. Right, so it improved both of them, so that is good.